Hi students, let us see the basic fundamental laws of electromagnetism that pave way for Maxwell to frame the equations for electromagnetic waves. The fundamental laws are Faraday's law, Lenz's law, Ampere's law, Gauss's law. These laws include the magnetic field due to the steady currents, the electromagnetic field due to quasi-stationary current, and the study of electric field due to static charges. All these laws led to the development of Maxwell's equation of electromagnetic waves. With these laws, Maxwell was able to predict the possibility of propagation of electromagnetic wave through space. Maxwell also derived a set of partial differential equations that gives the relation between the sources and the magnetic vectors. Now let us consider a coil connected with a galvanometer and a bar magnet NS placed close to it. If there is no relative motion between the coil and the magnet, the galvanometer indicates no current in the coil. On moving the magnet towards the coil, the galvanometer shows a deflection. This indicates the generation of current in the coil. The deflection persists so long as there is a relative motion between the coil and the magnet. The magnet is moved away from the coil, the same results are obtained, excepting that the direction of deflection in the galvanometer reverses. And now let us understand the concept of electromagnetic induction by the previous experiments. Whenever there is a change in magnetic flux linked with a circuit of the same type, an electromotive force is produced. The electromotive force is known as the EMF. This EMF is known as the induced EMF. This phenomena of producing an induced EMF due to the changes in the magnetic flux linked with a circuit is known as the electromagnetic induction. With this phenomenon of electromagnetic induction, Faraday framed two laws. The first, Faraday's law of electromagnetic induction, states that whenever there is a change in the normal magnetic flux linked with a circuit, an EMF is produced. This induced EMF lasts so long as the change is taking place in the circuit. The second, Faraday's law, states that the magnitude of the induced EMF is proportional to the rate of change of magnetic flux linked with the circuit. This shows the mathematical expression for Faraday's law. The equation has the electromotive force E, which is equal to the product of the number of turns linked with the coil and the instantaneous change of flux with that time in the circuit. Lenz's law. This law gives the direction of the induced EMF produced in the circuit, and that EMF will always oppose the change which is responsible for its production. If you see in this diagram, if the magnet moves towards the coil, there is an in the magnetic flux, and that magnetic flux will be opposed by the resisting force which is produced during the induced EMF. Likewise, if the magnet moves away from the coil, then the resisting force so produced will oppose and will decrease the magnetic flux linked with the circuit. Let us see the Ampere's circuital law. Whenever there is a current flow in a coil, the production of magnetic field inside the circuit is governed by the Ampere's circuital law. The statement gives that the line integral of the magnetic field around a closed curve is equal to the product of probability of free space mu naught and the current J, or the current density around that path of integration and which is passing through the circuit. So we have the closed integral B dot TL is equal to mu naught into I. Gauss's law relates the flux through any closed surface and the net charge enclosed within the surface. The statement goes on like this: the flux of the electric field E to any closed surface equals to the total net of charge inside the closed volume divided by epsilon naught. The expression is the closed integral over E dot ds is equal to 1 by epsilon naught, the total quantity of the charge enclosed in that particular volume. With the fundamental concepts and fundamental laws of electromagnetic induction, a new phenomenon of electromagnetic wave motion and radiation were developed by Maxwell. Maxwell derived a set of partial differential equations describing the relationship of the sources and the field vectors. Accordingly, he derived the differential form and the integral form and was able to interpret the basic laws behind it. These equations were as follows. The differential form of equation 1, both differential and integral form of equation 1 interprets Gauss' law applied to the electrostatics. Accordingly, it is divergence D is equal to rho and closed of D dot ds is equal to integral of rho into dV. The equation 2 interprets the Gauss' law for magnetic fields, that is divergence B is equal to 0 and closed integral of B dot ds is equal to 0. The third equation interprets Faraday's law of electromagnetic induction, that is the curl E is equal to minus of dou B by dou T, and the integral form of the same equation is closed integral of E dot dl is equal to minus of closed integral of dou B by dou T into ds. The E4 interprets the Ampere's law for a magnetic field produced by a current, that is the curl H is equal to J plus integral of dou T by dou T, and closed integral of H dot dl is equal to integral of J plus dou D by dou T of ds. Let's see the significances of Maxwell's equation. It firmly establishes the wave theory of light, and it showed that the electromagnetic waves travels with a velocity which is equal to the velocity of light. Light waves are also electromagnetic waves in character and bases assumptions that matter has no atomistic structure and it is always continuous. Essentially, it describes the macroscopic phenomena related to electromagnetic waves.